Alright, and here we are back in parallel RL circuits. And I know that I said we were done with parallel RL circuits and RL circuits in general, but I decided to go ahead and do a fault in a multi-component branch so you could see what those look like. We'll keep this fairly brief. We're going to start this one, the resistive inductive one, with it open. So L1 is open. And with L1 open, we know that all of the changes in the circuit are going to be happening in branch 2. Because if L1 is open, then it has maximum resistance, and if it has maximum resistance, then that branch has maximum resistance. It's no longer a conducting branch. If it has maximum resistance, it has zero current. So all of our current is now the current through branch 1 and branch 3 combined. Alright, so let's take a look real quick at the math. So obviously the ohmic value for L1 is going to go from its original 10.21K to maximum. Now, the ohmic value of L2 is not going to change, but the ohmic value of the branch is going to be driven to the value of L1, which is maximum, right? The larger of the two there. It doesn't matter what you add to maximum, it's still going to be maximum, right? Too large for current to overcome. Alright, the ohmic value for our inductor 3 is not going to change. It will stay 11.78K. And then when we combine those values together to get a total inductive reactance, we find that it is actually 11.78K. That is because our maximum value drives our reciprocal to that lowest value, which in this case is the ohmic value of branch 3, which is 11.78K. Now, you don't even have to do the math for this, but if you were to, you could give it some large number, like 3 meg, right? And we've done this before in resistive circuits, right? We took a look at the math, and we saw that if you have a smaller number and you add something very large, then it drives it to that lower value. It's kind of the same idea of what's happening when you are meter loading. Okay. So we have a total inductive reactance of 11.78. This is, of course, going to change our impedance, right? If we have now a larger ohmic value for our inductive reactance, we are expecting our total impedance, right, our impedance up there to go up. And it does. It goes up to 7.15K. Now, if impedance is going up, we're expecting current to go down, and we could have predicted that in advance, right? Because if I originally had 3 branches of current, but now I only have 2 branches of current, it makes sense that current has gone down. And then if you weren't looking at it in the ohmic value way, if you were just looking at current, if you know that current went down, you obviously know that impedance went up. Okay. So our current changed and it went to 2.52 milliamps, so down, which is the combination, of course, of branch 1 and branch 3. So if we put our new values into our current formula, we will find that we come up with a number that is very close to 2.52 milli. In fact, it's probably within 1 or 2 hundredths. All right, now the voltages, of course, the voltages to the branch will be the same. So branch 1 will have 18 volts, branch 3 will have 18 volts, branch 2 will have 18 volts. However, we see our voltage across our open. So 18 volts is applied to branch 2. But if we read, so if we read from the top of branch 2, right here, to the bottom of branch 2, we would read 18 volts because we are essentially reading across our power supply. However, if we put our red lead right here in between L1 and L2, and then left our black lead down here on this side of L2, we are on both of our leads are on the one side, right? They're not straddling the open, and if they're not straddling the open, we will read a 0 potential difference. Now, if we were to move our reference lead and put it in between L1 and L2, and put our red lead up here at the top of the branch, then we would be reading across our open, and then we would see applied voltage of 18 volts. So in actuality, if you were to look individually at these branch components, we would see that L1 is 18 volts and L2 is 0 volts, right? No current flow, and it's not where the open is, so it's 0 volts. L1, of course, has the 18 volts because it is where our open is. Alright, and next we are going to look at a short in a parallel RC circuit.